Hello and welcome back to Introductory Astronomy. Now, the next time you admire the night sky, I want you to recall that every star you see is part of the star system in which we live. You will learn in this chapter how evidence reveals that we are inside a great wheel of stars, a galaxy. This galaxy is called the Milky Way galaxy, and it is over 80,000 light-years in diameter and contains more than 100 billion stars. It is our galaxy because we live in it, but we're also a product of it because the stars in the Milky Way galaxy made many of the atoms in our body. We begin this chapter by pondering the notion that the stars belong to us, but when we reach the end of this chapter, you may realize that we also belong to the stars. In this picture right here, we see a galaxy known as M51, or the Whirlpool Galaxy. It contains about 100 billion stars bound together by the force of gravity. The graceful winding arms of this majestic spiral galaxy sweep across 100,000 light-years of space. The whole object is about 33 million light-years away from us. Its size, shape, and mass approximate those of our own galaxy, which has never been photographed in its entirety because we live inside it. If this were our galaxy, the Sun would reside in one of its spiral arms, 2/3 of the way out from the center. In this chapter, we're going to talk a little bit about our own galaxy, general galactic structure, the formation of the Milky Way, the formation of the galactic spiral arms, the mass of our galaxy, and the galactic center. If you take a look at frame A, gazing from Earth, our planet, toward the galactic center, the white arrow, in this artist's conception, we see myriads of stars stacked up within the thin band of light known as the Milky Way. Looking in the opposite direction, the blue arrows, we still see the Milky Way band, but now it is fainter because our Sun lies far from the galactic center, so we see more stars when looking toward the center than when looking in the opposite direction. Looking perpendicular to the disk, the red arrows, we see far fewer stars. Frame B, we have a real optical view of the sky all around us. The white band is the disk of our Milky Way galaxy, dimly seen with the naked eye from very dark locations on Earth. This is what one sees looking towards the galactic center, in the direction of the white arrow in frame A. Let's take a look at the Andromeda galaxy structure, since it is similar to our own spiral galaxy. In frame A, we see the Andromeda galaxy, which we believe fairly resembles the overall layout of our own Milky Way galaxy. The disk and bulge are clearly visible in this image, which is about 30,000 parsecs across. The faint stars of the halo completely surrounding the disk and bulge cannot be seen here. The white stars sprinkled all across this image are not part of Andromeda's halo. They are foreground stars in our own galaxy, lying in the same region of the sky as Andromeda, but about 1,000 times closer. Frame B, we see more detail within the inner parts of the galaxy. And in frame C, we see the galaxy's peculiar and still unexplained double core. This inset covers a region only 15 parsecs across. Here we have pictures of two more spiral galaxies. In frame A, we have a galaxy cataloged as M101, and it is seen nearly face-on. It is somewhat similar in its overall structure to our own Milky Way galaxy and the Andromeda galaxy. In frame B, we see the galaxy NGC 4565, which happens to be oriented in such a way that we see it edge on, allowing us to make out its disk and central bulge. One of the first attempts to measure the Milky Way was done by Herschel using visible stars. Here is Herschel's galaxy model. He constructed this map in the 18th century by counting the numbers of stars he saw in different directions of the sky. Our own sun, marked by the large yellow dot, appears to lie near the center of this distribution. The long axis of the diagram lies in the plane of the galactic disk. Unfortunately, Herschel was not aware that most of the galaxy, especially the center, is blocked from view by vast clouds of gas and dust. We have already encountered variable stars, novae, supernovae, and related phenomena. These are given the special name of cataclysmic variables. Now, there are other stars whose luminosity varies in a regular way, but much more subtly. These are called intrinsic variables. We have two types of intrinsic variables, the RR Lyrae stars and the Cepheid stars. The upper plot is an RR Lyrae star. All such stars have essentially the same luminosity curve with periods from 1/2 to a whole day. The lower plot is a Cepheid variable star. Cepheid periods range from about 1 to 100 days. The variability of these stars comes from a dynamic balance between the force of gravity and pressure. They have large oscillations around stability. So if you take a look at the HR diagram here, pulsating variable stars are found in what we call the instability strip of the HR diagram. As the high-mass stars evolve through the strip, it becomes a Cepheid variable. Low-mass horizontal branch stars in the instability strip are called RR Lyrae variables. The usefulness of these stars comes from their period luminosity relation. If you take a look at this plot here, we have a plot of pulsation period versus average absolute brightness, meaning luminosity, and this represents a group of Cepheid variable stars. The two properties are quite tightly correlated. As you can see, as the luminosity is increasing, so is the pulsation period. You can also see the pulsation periods of some RR Lyrae variables on their lower left corner. This allows us to measure the distances to these stars. RR Lyrae stars all have about the same luminosity. Knowing their apparent magnitude allows us to calculate the distance. Cepheid stars have a luminosity that is strongly correlated with the period of their oscillations. Once the period is measured, the luminosity is known and we can proceed as above. This is very useful because we have now expanded our cosmic distance ladder one more step. So the application of the period-luminosity relationship of Cepheid variable stars allows us to determine distances out to about 25 megaparsecs with reasonable accuracy. Many RR Lyrae stars are found in globular clusters. These clusters are not all in the plane of the galaxy, so they're not obscured by dust and can be measured. This yields a much more accurate picture of the extent of our galaxy and our place within it. Take a look at the picture right here. Our sun does not coincide with the center of this very large collection of globular clusters, which is indicated by the pink dots. Instead, more globular clusters are found in one direction than in any other. The sun resides closer to the edge of the collection, which measures roughly 30 kiloparsecs across. The globular clusters outline the true distribution of stars in the galactic halo. Let's take a look at Discovery 23-1, Early Computers. Much of the early detailed work in astronomical research was done by analysis of photographs. This work was mostly done by women called computers, as they did computations. Several of these women went on to become well-known astronomers in their own right. Their work enabled the advances made by Shapley, as well as Hertzsprung and Russell, among others. Some of their discoveries and innovations that were made by them was the spectral classification system, oh boy, an F grade kills me, and the period luminosity relationship of Cepheid variable stars. And your book goes in a lot more detail about these women. Let's talk a little bit about the galactic structure. This is an artist's conception that shows the various parts of our galaxy and the position of our sun. It's a nearly edge-on view, and it shows schematically the distributions of young blue stars, open clusters, old red stars, and globular clusters. Notice how the brightness and size of our sun are greatly exaggerated for clarity. The galactic halo and globular clusters formed very early. The halo is essentially spherical. All the stars in the halo are very old, and there is no gas and dust. The galactic disk is where the youngest stars are, as well as the star-forming regions, emission nebulae, and large clouds of gas and dust. Surrounding this galactic center is the galactic bulge, which contains a mix of older and younger stars. This is an infrared view of our galaxy, and it shows more detail of the galactic center than the visible light view does, as infrared is not absorbed as much by gas and dust. Stellar orbits in our galaxy. Stars in the galactic disk, blue curves, move in orderly circular orbits about the galactic center. In contrast, halo stars, the orange curves, have orbits with largely random orientation and eccentricities. The orbit of a typical halo star takes it high above the galactic disk, then down through the disk plane, and then out the other side and far below the disk. The orbital properties of bulge stars are intermediate between those of disk stars and those of halo stars. Study sections 23.1 through 23.3. Be able to describe the overall structure of the Milky Way galaxy, and be able to explain how variable stars are used in determining the size and shape of our own galaxy.